This is a lesson in calculus-based mechanics on the vector quantities of the center of mass. We'll start out with the position of the center of mass, but include also the velocity and the acceleration. This is in the mechanics and momentum unit because we are going to use the velocity of the center of mass in order to calculate quantities in momentum with elastic collisions. But while we're on the topic, we're going to explore the location of the center of mass as well as the acceleration of the center of mass. Might as well while we're here. And what I'm going to do is just start us off with the easiest way to think about the position of a center of mass of multiple objects. All right, we're just going to start off simple here and think about if I have multiple objects, and I have a good example of course, is the weighted average of each individual object's position. So if I want to find the location, and we're going radius here, this could be an x value or a y value, etc. M1, R1, sorry about that, I can fix that on the fly here. M1, R1 plus M2, R2 plus, and if we have multiple objects, if we have a bunch of objects, 4, 5, whatever, we can go up to n. So this equation divided by m total, this formula isn't too hard to use as long as you have well-defined objects, and this radius, this location for each individual object is for the center of mass of each object. So we're going to have well-defined objects and just look at where each center of mass of each object is and weight it by each mass. So if we have a larger object, then that radius is going to get a larger weighting. And we do this in statistics. If you've had statistics, this may look like a weighted average equation to you, but now we're using it with vectors in physics. And what I'm going to note here also is that we must assign a coordinate system. This is a vector quantity, so we must assign where the origin is and measure everything from the origin. So let's do a quick example here. I picked out from the OpenStax University Physics Volume 1. I think it's a back of the chapter problem. So it says find the center of mass of a sphere of mass big M and radius big R, and a cylinder of mass little m, radius little r, and height little h. All right, so those are the dimensions, and I'm going to remind you that we know where the center of mass of a uniformly distributed, we're going to assume that they're uniformly distributed masses in the sphere and in this cylinder. So they will be at the geometric center of each of these objects. I'm going to start off initially, and what I'm going to notice is that the center of mass is going to be along an axis down the center of these two objects, down here. The x position, if I assign a coordinate system here, the x location is going to be in the center, but I'm more interested in the y location of the center of mass of this system of objects. So when I look at the system of objects, I need to know where is their individual center of mass. So that's easy. Like I said, it's well defined for these objects. It will be the geometric center of the cylinder and the geometric center of the sphere. Okay, so when I look at this, the geometric center of the cylinder is going to be a half h from its bottom, so that's not too bad. The geometric center of the sphere, you may see the game I'm playing here about finding these locations, is going to be a whole h, the height of the cylinder, plus the radius of the sphere. Okay, so that's the information we need for the locations of the center of mass of each individual object. So I'm going to add this up, the y of the center of mass of this system. We're in the positive y direction. I'm not going to worry too much about signs here. So the cylinder is going to be a little m for its mass, and its R location is a half h, like we had pointed out. And then I'm just going to add on the mass of the sphere multiplied by its height. its location in the y direction for the center of mass. And then I'm going to divide by big M plus little m. All right. That's it. That is it. I think if you wanted to simplify this equation, you could simplify it a little bit more. It depends on what purposes you're using it. We don't have any numbers. I'm going to notice that there's an h in this first term and an h in the second term. So I'm just going to gather that together. So I get h a half m plus a big M, and then a big M over R times R, and then that is still over the total mass. And I'm just going to leave it like that for now. We're working with symbols, and that's as simplified as I want to get it for right now. That's how you use that equation. Let's do it again on a different orientation here. Same thing we're going to do. We can assign our coordinate system x in that direction. I'm going to go with the y-axis through the center of masses of each so that we're symmetrical in the x direction. There is a z direction here due to the geometry of these objects, but symmetrically the x and y are along the axis in the center here. Y is the only one that varies with position. So here's the center of mass of the cylinder, the center of mass of the sphere. I'm going to do the same thing I did before. This distance is going to be a little r, the radius of the cylinder. This distance here is going to be, what is that? Well, that's going to be 2 little r's plus a big R here. 2 radii of the cylinder, and then 1 radius of the sphere. So let's do this again. Y center of mass. We're going to have little m times little r plus big M, 2r plus big R. And we're going to weight it by, divide by the total mass. And that's it. Like we did on the previous example, we can simplify this a little bit. There's an R in the first and second term, so I can gather those up. So I have R, M plus 2 big M's plus MR. I don't know if that's any simpler, divided by the total mass. And that's it. That's how you use that equation. If you have simple, well-defined, uniform objects that you know where the center of mass is in a coordinate system. Of course, this is calculus-based, and we can make this a little bit more complicated. So what we can do is look at this in regard to an integral, where I have a non-uniform mass distribution. You can imagine that I may have a weirdly shaped object. Let's see, I don't know what this is. I just made it up. And you can see that even if the mass is uniformly distributed throughout this object, it has a weird geometry. So the center of mass is going to be oddly, not in the geometric center, whatever that means for this object. And especially if the mass term, it has a weird distribution in either dimension of this object in the x or y direction. Like it may be heavier at the top than it is at the bottom. So I would need to know how the mass is distributed across the location of this object in order to do this integral. And I've map that out down here. All right, so we sort of have the same form as before. The center of mass is a weighted average of the radii for each individual mass, and here we have a dm, not a well-defined m, but a differential of mass. We're still dividing by the total mass, but we're going to integrate over this differential of mass. And again, we need to define a coordinate system. That's the easy thing about this problem. The hard thing about this problem for you is probably going to figure out the differential for the mass. And I'm going to remind you that mass is, right, density is mass divided by volume. If I have a differential of mass, I'm going to have a differential of volume. And so I do some algebra on that. The density, typically that's what changes as a function of location, is the density. And then I can multiply by the differential of volume. If there's only one dimension, so for example, if I only have a differential, the density depends only in the x direction, I'll have rho x dx, and then I'll just have a y and a z in here. Sorry about that. The differential in the x and the y and the z directions won't matter to me, right? If the density is distributed non-uniformly only in the x dimension. So that's the type of problem I've chosen. If you do this y times z, well, that's typically an area. And this is a volumetric density, so I would need to multiply overall by a volume. So area times a differential of x is a volume. On the next problem, though, the problem that I've chosen for you, we are given what is called a linear mass density, where I'm not given a rho overall, I'm given a lambda, which means that the density depends only on the x dimension. So when I do this, I'm not going to worry about the other two dimensions. I'm just going to worry about the x dimension only. And that's fine, because if I have a rod, I don't care about the location of the y, and I don't care about the location of the z. I really only care about the location of the center of mass in the x direction, which is going to be weighted more on the heavier end. You can see that as x gets larger, the object gets heavier on this end in regard to mass. Okay, so let's read the problem here just to get a little bit oriented. A 3-meter long rod, which we can see that on the picture here. It's well defined for us with a coordinate system. With one end at the origin and extends along the x-axis. Okay, the linear mass density, mass per unit length, varies with position. Lambda of x is 0.65 x cubed, where lambda has units of kilograms per meter when x has units of meters. So when we find the center of mass, it'll be in meters. Where along the x-axis is the rod's center of mass. Okay, so how do I set up this differential? And what we're going to do is, I'm not going to worry so much about r here for a second. I'm going to look at dm. Okay, let's look at dm. What is dm? The differential of mass. Okay, so I know that the differential mass, I wrote on the previous slide, if I have a mass density, I'd take the mass density as a function of all of this stuff and then multiply by a dV. But that's not what I have in this situation. The differential of mass is going to be the linear mass density, which is a function of x. And then I'm going to multiply that by dx, right? Because that's the dimension over which the linear mass density depends. Okay. If I do an integral on both sides, let's do an integral on both sides. And I haven't well defined this yet. I'll get the mass equals, well, I guess I could well define it. It's from 0 to 3 meters, right? My x extends from 0 to 3 meters. Lambda of x is going to be 0.65 x dx. Okay. Well, I need a cube in here in order to properly recopy my function. And that looks manageable. This is just a integral, a power rule integral over one dimension from 0 to 3. I don't even have to do the math on the one end. So let's integrate this. 3 plus 1, well, that's a 4. So I get 0.65 divided by 4, x to the 4th, evaluated from 0 to 3. So what this is going to do is give me the total mass, right? And we need the total mass for the problem. So m total will equal 0.65 times 4, or divided by 4, 3 to the 4th power. And when you multiply this through, you get 13.1625 kilograms. So I have the total mass. If you need the total mass, there's the total mass. I'm going to reserve this version of it to use later, and you'll see in a second why that's true. Okay, so that's the total mass. I'm not done with the integral yet. What I'm going to do is now I'm going to set up the integral. Now that I have the total mass, let's fill in the rest of this problem. Well, our center of mass, I don't have an r, I have an x of the center of mass, right? Equals the integral of r dm over total mass. So let's do this. I'm going to have the integral from 0 to 3 of r, which for all my intents and purposes, r is just going to be x, right? Whatever location that center of mass is, it's just going to be an x location. So I'm integrating x times dm. Well, I already wrote out what dm. dm is lambda as a function of x dx. So I'm going to take x times 0.65 x cubed dx. And I'm going to keep that over m total. Okay, so that's how I'm going to set up this integral. You're going to notice that I have x and x to the third. So when I simplify this, I'm going to get the integral from 0 to 3 of 0.65 x to the fourth dx over m total. Okay, so we're ready to do this integral. X to the fourth, well, if I add 1, I get to the fifth power. And you'll like this, so I get 0.65 x to the fifth power over 5. I still need to bring that 5 down. Evaluated from 0 to 3. Divided by 0.65 divided by 4. So that's why I said I'm going to reserve this version of it in order to use later, m total. And you'll see here in a second why I did that. Do you see that? How all of this simplifies? The 0.65s cancel. Some x's cancel. That one goes away. So I get 4/5 x evaluated from 0 to 3. You're okay if I do that? Which is actually just 4/5 times 3. All right, well, that's not too bad. 0.8 times 3, well, I know how to do 0.8 times 3. I didn't even have to get my calculator out for that one. 2.4 meters, and that is where the center of mass for this non-uniform rod is. Okay, so when you're setting up this integral, there's two things you need to do. M total, you have to figure out the total mass. That's an integral. And then you also have to integrate where the weighted average of this center of mass is across, considering the linear mass density multiplied by position. So that's how to do that problem. If you were to do this for velocities, you could do that. You know, velocity may depend on position. But the way we're going to do this with center of mass velocity with multiple objects is we're just going to let each mass be a well-defined mass with a well-defined center of mass and have a constant velocity. So we'll just write out here v equals constant for each one of these masses. And you're going to note that this is very similar as to the position equation for the center of mass. It's a weighted average of each individual object's velocity rather than location. And again, we're assigning coordinate system. If an object is moving in the negative direction, we'll have to take that into account in the weighted average. So I'm not going to belabor that anymore. Let's do an example. Two particles are moving in the xy plane. Mass 1 is 2 kilograms and has a velocity, they give us in components here, 3I plus 5J meters per second. Remember, I is in the x direction and J is in the y direction. And the other mass is 3 kilograms with 6I minus 2J meters per second. Determine the velocity of the center of mass. Give magnitude and angle with respect to the positive I. Okay, so magnitude and angle. When we use this equation, because they gave us vector components, we'll get vector components out of the V center of mass, and then we can use those vector components in some trig in order to find out the magnitude and angle. Okay, so that's the general strategy. So let's just do the first part here, V center of mass. I'm going to assume that they assign Cartesian coordinates with x and y in this direction. That's all I'm going to assume. There's positives and negatives in these components. So I'm just going to do the formula here. M1 is 2. Its velocity is 3I plus 5J. All right. That was easy. And then I'm going to add on the second masses, mass times velocity, 6I minus 2J. And then I'm going to divide by the total mass, 2 plus 3. Okay, so that's not too bad. Just plug those into the formula. Let's distribute here and gather up terms. I have a 6I plus an 18I plus a 10J minus a 6J. Okay, divided by 5. So I can simplify that. 6 plus 18 is 24 fifths I hat plus 10 minus 6, 4 fifths J hat. And that's the meters per second. So that's the velocity of the center of mass in Cartesian coordinates. But that's not what we want. They want the magnitude and angle. So I know how to do this. If I want the magnitude of the velocity of the center of mass, which I'm just going to call V center of mass with no accents or brackets or absolute values or anything, I'm going to take the square root of Pythagorean theorem, right? 24 divided by 5 squared plus 4 divided by 5 squared. All right. You can do your fancy algebra on this, gather up terms, take them outside the radical or whatever you want to do. But when I run this through the calculator, the magnitude of this velocity of the center of mass is 4.9. There's some decimals and sig figs here that you can calculate if you need them, but that's the velocity of the center of mass. Right? Pretty easy. We've been doing this since the beginning of the course, is resolving a vector given its components. And when I look at this, the x component of this guy is 24 fifths, which is almost 5, 24 fifths in the x direction. And then it's a positive 4 fifths in the y direction. So we found the length of this hypotenuse, but we still need to find the angle. I'm going to notice that tan of this angle is 4 fifths divided by 24 fifths. 24 fifths. Okay, 5s cancel. I like when things cancel out. 24 over 4, well, that's 1/6 even. So when you plug in the inverse tan of 1/6 into your calculator, you get from the positive x-axis, or positive I hat, it says, I get plus 9.5. You can do sig figs if you want, degrees above the x-axis. So same procedure, assuming constant velocity, we have a very easy formula equation in order to plug through, and then we pulled up our prior knowledge about resolving vectors into a magnitude and direction. So that's velocity. We're gonna keep that technique in our pocket for when we move to elastic collisions and momentum. So we'll put a pin in that for now for another lecture, but I wanted to move on to the center of mass acceleration. You may not be surprised to see the same form of this formula equation here for the center of mass. The weighted average of each individual object's acceleration. We're going to assume the acceleration is constant for each individual object. We're going to assign a coordinate system. We're going to do a weighted average of each individual's acceleration and divide by the total mass here. And I have a little bit interesting example. Two objects are accelerating along the x-axis. Object P, which is 10 kilograms and 5 meters per second squared, accelerates towards object Q, 15 kilograms meters per second squared. Determine their center of mass acceleration if they are heading toward one another, away from one another, and in the same direction. So it says toward twice here. I think that may be a little bit confusing, but let's just draw a picture here. If they're heading towards each other, object Q is accelerating towards object P. Let's just go with the simplest thing here where there's P and there's Q. P and Q. I'm going to note that Q is a little bit larger than P, but that's fine. And this guy has an acceleration of 5, and this guy has an acceleration of 3. So good thing that we remember that we need to assign a coordinate system. I'm going to say positive x is in that direction to the right. I don't know. You could have chosen to the left. It doesn't matter as long as it's well defined. So now we can set up our acceleration of the center of mass equation. Each mass has its own acceleration, and we need to take the vector into account. So the first mass is 10, and it's accelerating at 5 meters per second squared. The second mass is 15, and it's accelerating at -3, right, in the negative direction. And then I'm going to divide by the total mass, which is 10 plus 15. So 50 minus 15 times 3 is 45, divided by 25, so I get 5 over 25, which is what, 0.2 meters per second squared in the positive direction as I've defined it in this problem. Okay. So pretty straightforward. Let's do the next example here. I have P and Q, and they're accelerating away from each other. I don't know if they can accelerate towards each other and away from each other at the same time. It seems like here, let's go P, let's make P go in the negative direction and Q go in the positive direction. That's what makes sense to me. I don't think they can accelerate towards each other and away from each other at the same time, but we'll keep working with this. Positive x, define my coordinate system, set up my situation here, my formula, A center mass. The 10 is moving at -5, and the 15 is moving at a +3, and I still have the same total mass. So this looks very similar to the previous part, -50 plus 45 divided by that 25. So I see that the acceleration is a -0.2 meters per second squared, as defined in the coordinate system that I have. Okay, so watch out for your negative signs. You can see that we got a relative negative sign here. The last part here, last part of the last problem, here's P and here's Q. And so you're seeing that the sign makes a difference, and here they're heading in the same direction. So here's positive. I'm going to make them both go in the positive direction. They could be moving in the negative. It's not specific here. Just they're in the same direction. So P's moving at 5 and Q's moving at 3. How will this affect our A center of mass? Well, we don't have any negative terms anymore, so I have 10 times 5 plus 15 times 3. So I'm going to get a larger denominator on the larger numerator for this one. So I get 50 plus 45 divided by that 25 term. 50 plus 45, well, that's 95 divided by 25. So overall, I'm going to get a positive, and when you run this through your calculator, you get 3.8 meters per second squared. So when we do this weighted average, the acceleration of the center mass is they're contributing to the center of mass moving wherever this is. It's closer to Q, right? Q's the heavier one. So if I looked at the center of mass of the system, it's closer to Q, and it's moving in this direction. And it's weighted by both of them. So it's going to be faster than like here the center of mass is in the same location. There's the center of mass of the system. But I have a 5 in this direction and 3 in this direction, so it won't be as large as in the last situation here. So that's how to do some basic problems involving the concept of the center of mass vector quantities. Good luck and have fun.